discuss about the isoparametric element. How it differs from the other linear bar element and quadratic bar element means we can use this element for the curved shapes. It is difficult to analyze the curved shapes in finite element analysis, but using isoparametric element we can able to analyze the curved shapes in the finite element analysis. In today's class we are going to derive the derivation for the shape function for isoparametric element, and we are going to discuss how we have to convert the natural coordinate system into local coordinate system. In this we are going to convert the x and y into the natural coordinate system, so local coordinate system epsilon and eta. First of all, I am going to consider a 4-noded rectangular element. This is a 4-noded rectangular element. I consider a 4-noded rectangular element. The rectangle may be in the shape of also quadrilateral. So I am taking the nodes 1, 2, 3, 4. This is my element. It is in the Cartesian coordinate. That is, the one is represent x1, y1, x2, y2, x3, y3, x4, y4. It is in xy coordinate. We can consider any point P inside the 4-noded element. Now first I am going to do the transformation. I am going to transform this xy into the local coordinate epsilon and eta. How once it is converted into epsilon and eta, it has been going to convert it like this, and also we are going to have similarly node 1, 2, 3, 4, but it is in the terms of epsilon and eta. We already know that the advantage of natural coordinate system is the values of the nodes will be ranges from -1 to +1. So for the node 1 I am going to take it as -1, -1. For the node 2 I am going to consider as -1, +1. For the node 3 I am going to consider +1, +1. For the node 4 I am going to consider -1, +1. Sorry. For node 1 we are considering it is in the third quadrant, so we are considering -1, -1. The node 2 we are considering as +1, -1. Since it is in x is positive and y is negative, in the third quadrant we are considering both as positive, and in the fourth quadrant we are considering the x is the negative and y is the positive. That is epsilon eta. The epsilon, the natural coordinate ranges from +1 to -1, and the point P we are going to convert this point P. Now our objective is to find the shape function. Now I am going to derive the shape function for node 1. For node 1, the shape function n1 equal to some constant into 1 minus epsilon, 1 minus eta. This is from the serendipity elements. That is, it is used to derive the shape function for higher order elements. As I already told, the isoparametric element is a higher order element. Since we are having, if we are derived using xy coordinate, then we will have a0 plus a1x plus a2x square plus a3x cube. So we are having up to x cube term. So if we derive using xy, then we will get more and more complex. That's why we are transforming the xy coordinate into epsilon eta. The first we have derived, now we have transformed, first part to review this. We have transformed the 4-noded rectangular element into the parent element. Then using this parent element, I have wrote the shape function for the node 1. n1 equal to some constant into 1 minus epsilon, 1 minus eta. Now we have to substitute the boundary condition. We already know that at node 1, at the particular node, the shape function n1 is 1 and the value of epsilon equal to -1, eta equal to -1. If I substitute in this, 1 equal to constant into 2 into 2, then I will get the constant equal to 1 by 4. So that the shape function n1 equal to 1 by 4, 1 minus epsilon, 1 minus eta. So this is the shape function for node 1. Similarly, we have to do for the node 2, node 3, node 4 respectively. Now I will do the for node 2. Similarly, for node 2, I am going to note as plus epsilon 1 minus eta. Then I am going to substitute the boundary condition. At node 2, we are going to have n2 as 1 and epsilon equal to plus 1 and eta equal to minus 1. So that we can substitute 1 equal to some constant into 2 into 2. So the constant value is 1 by 4. So we got the value of n2 equal to 1 by 4, 1 plus epsilon 1 minus eta. So this is the shape function for n2. Similarly, for n3 and n4, we can write directly n3 equal to 1 by 4, 1 plus epsilon 1 plus eta. And for n4, 1 by 4, 1 minus epsilon 1 minus eta. Now students, I am going to say shortcut how to remember this n1, n2, n3 and n4. If you notice that the parent element which we have to, the parent element, now I am drawing only the parent element which we have to in terms of local coordinate epsilon and eta. The first point, the first node actually, the first node 1 is minus 1 comma minus 1, the second node is 1 comma minus 1, the third node is 1 comma 1, the fourth node is minus 1 comma 1. If you notice that this is the shortcut, you have to use this minus 1 comma 1. For example, while writing n1, n2, n3, n4, the common term you have to use is 1 by 4. Then I am saying this in the terms of epsilon and eta, you can put 1 minus epsilon, 1 minus eta. Similarly, for this 1 by 4 into 1 plus epsilon into 1 minus eta. For the third shape function, 1 by 4 into 1 plus epsilon into 1 plus eta. Shape function for n4 equal to 1 by 4 into 1 minus epsilon 1 plus. Now we have derived the shape function n1, n2, n3 and n4 for the 4-noded rectangular element using the natural coordinate system. We have used the epsilon and eta, we are not using x and y coordinates. In first 3 or 4 units we have used only xy, everywhere we have used xy. But here what we are doing is we are using only epsilon and eta. Then after deriving this, we are going to write it in the form of a displacement variable. We all know that each node is going, since it is a 2-dimensional problem, each node is going to have 2 field variables. So that is 2 displacements. For example, the node 1 is going to have the displacement in x direction, we will say as u, in y direction we say as b. The u is the displacement in x direction and y is the displacement in, b is the displacement in y direction. Similarly, the node 2 is also going to have 2 displacements, node 3 is also going to have 2 displacements, the node 4 is also going to have 2 displacements. Totally we are having 8 displacements. How we are going to write the displacements is u equal to n1 u1 plus n2 u2 plus n3 u3 plus n4 u4. Similarly, v equal to n1 v1 plus n2 v2 plus n3 v3 plus n4 v4. While we are writing in the format of matrix, I am going to write the displacement field variable uv equal to, then we have to take the variables u1, v1, u2, v2, u3, v3, u4, v4. In the first equation we are having u1. The coefficient of u1 is n1. We are not having v1 in the first equation, so put 0. Similarly, n2 0, n3 0, n4 0. 0 n1, 0 n2, 0 n3, 0 n4. Now we have derived the shape function for the 4-noded, and we have wrote in the format of the displacement variables u and v. If I want to write in the format of Cartesian x and y, then you can write similarly in terms of u, you can use x, if in terms of v, you can use y. For example, now I am writing in terms of Cartesian coordinate x and y. They are asking you to write in the Cartesian format, means you can able to write it also in the format of Cartesian x and y. X equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. Y equal to n1 y1 plus n2 y2 plus n3 y3 plus n4 y4. So this is the format if they ask in the format of Cartesian. Next we are going to see how the transformation going to take place between the x and y and epsilon eta. So for this we are going to use the Jacobian transformation. Now I am going to derive the Jacobian transformation matrix. How? Means first I am going to take a field variable. Let f be the field variable. I don't know the f be the field variable. It may be a displacement or temperature, whatever may be. The field variable is common. That the term which is you are going to find using this element is called field variable. So I have taken f as the field variable. So f is the function of x and y. Then what we did? We have converted the x and y into epsilon and eta. So f is the function of x. X is the function of epsilon and eta. Similarly, y is the function of epsilon and eta. Then differentiate the f with respect to epsilon. Dou f by dou epsilon equal to dou f by dou x into, we are going to do the partial differential equation since the x depends on two variables and y also depends on two variables. Dou x by dou epsilon plus dou f by dou y into dou y by dou epsilon. Similarly for dou eta, dou f by dou eta equal to dou f by dou x into dou x by dou eta plus dou f by dou y into dou y by dou eta. Now we have to find what is this xy. Next what I am going to do is I am going to write it in the format of matrix. Here if you notice that dou f by dou x is common in both the equations. Dou f by dou y is common in both the equation. This side, in the left hand side, we are having dou f by dou eta, dou f by dou epsilon. Now I am going to write this in the format of matrix. Dou epsilon by, dou f by dou epsilon, dou f by dou eta. I am writing in the matrix format. I am getting. So the common term which we are having is, already we have said the common term we are having here is dou f by dou x and dou f by dou y. Dou f by dou x, dou f by dou y. The coefficient of dou by dou x is dou x by dou epsilon. Similarly, dou x by dou, for dou f by dou y, we are having dou y by dou epsilon. Similarly, dou x by dou eta, the second equation, dou y by dou eta. So this is the transformation that take place. We are going to consider this as a J matrix, which is said as Jacobian matrix. Jacobian matrix. Now I am going to take it as a similar format. J equal to dou x by dou epsilon, dou x by dou eta, dou y by dou epsilon, dou x by dou eta, dou y by dou eta. This is I am saying as J11, J12, J21, J22. Now I have derived what is the Jacobian matrix. I have defined the Jacobian matrix as J11, J12, J21 and J22. Now we are going to derive what is J11, J12, J21 and J22. J11, I will do only the J11. The similar procedure should be followed for J12 and J21 and J22. J11 equal to dou x by dou epsilon. We know that x equal to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4. We have to differentiate the x with respect to epsilon. We are having epsilon in n1, n2, n3 and n4. So you have to substitute n1, n2, n3 and n4. 1 minus epsilon, 1 minus eta instead of n1 into x1 plus 1 by 4 into 1 plus epsilon 1 minus eta into x2 plus 1 by 4 into 1 plus epsilon 1 plus eta into x3 plus 1 by 4 into 1 plus epsilon 1 minus epsilon 1 plus eta into x4. Now what we have to do now? We have to differentiate the x with respect to epsilon. So dou x by dou epsilon equal to, while I am differentiating 1 by 4, here we are having 1 by 4 1 minus eta as a constant and x1 also a constant. Now we have to differentiate only 1 minus epsilon. If we are differentiating 1, we will get 0. Minus epsilon, we are going to get minus 1. So I am putting minus 1. Plus 1 by 4 1 minus eta x2 into 1 plus 1 by 4 into 1 plus eta x3 into, while we are differentiating 1 plus epsilon, we are getting 1 plus 1 by 4 1 plus epsilon x4, while I am differentiating 1 minus epsilon, I am going to get minus 1. So we are having the common term as 1 by 4. I am taking the common term 1 by 4 minus into 1 minus epsilon x1 plus 1 by 4 into 1 minus epsilon x2 plus 1. Sorry, we have taken the 1 by 4 commonly, so we have to write 1 minus epsilon x2 plus 1 plus epsilon into x3 plus, minus 1 plus epsilon into x4. So this is the value for J11. Similarly, we have to do for J12, J21, J22. Now I will proceed with, I will directly write the answer for J12, 21 and 22. Similarly, so J21 is implies, J12. The J12 implies dou y by dou epsilon. So what it indicates? It indicates instead of y we are going to substitute. We know that y equal to n1 y1 plus n2 y2 plus n3 y3 plus n4 y4. If you notice that instead of x we are having y, so we will get the same answer for J11 and J12, but instead of y we have to use, instead of x we have to use y. So J12 equal to, I am going to write 1 by 4 minus 1 minus epsilon y1 plus 1 minus epsilon y2 plus 1 plus epsilon y3 minus 1 plus epsilon y4. Then we have to write for J21. The J21 is dou x by dou eta. First we are going to, we know that what is the value of x. Then we know the step what is the value for x. Now I am going to differentiate the x directly. Dou x by dou eta equal to, I am going to differentiate with respect to eta. So I am taking the common term 1 by 4 outside, and we will have 1 minus eta into minus 1 x1 plus 1 minus epsilon, 1 plus epsilon into minus 1. Now I am differentiating with respect to eta. So I will get minus 2 plus, we will have 1 plus epsilon into plus 1 into x3 plus 1 minus epsilon into 1 into y4. So we got the values. Then for similarly, this is nothing but J21 equal to 1 by 4 minus 1 minus eta x1 plus 1 plus epsilon, minus into 1 plus epsilon into x2 plus 1 plus epsilon into y3 plus 1 minus epsilon into x2. So we got, similarly we can write for J22. The J22 is nothing but d dou y by dou eta. So we are going to write similarly, okay, instead of x we are going to put y. So J22 equal to 1 by 4 minus 1 minus epsilon y1 minus 1 plus epsilon into y2 plus 1 plus epsilon into y3 plus 1 minus epsilon into y4. Now I have derived the Jacobian matrix J11, J12, J21 and J22. This is Jacobian matrix. What is the advantage of this Jacobian matrix? As I already stated that using the Jacobian matrix we can able to the advantage of Jacobian matrix is we can convert the xy, that is Cartesian, can be converted to the local coordinates epsilon and eta. As I already told, the value of epsilon and eta, the values of epsilon and eta with the ranges from varies between -1 to +1. So this is the greater advantage. We are not having any value like 10, 20 like that. It varies from -1 to +1. So it is easier to compute the value with the computers, so that it is a very easiest technique in finite element method. So that's why we are using the Jacobian transformation. And also the memory required is very less, and we can use this technique for the complex geometry. For complex geometry we can use the isoparametric elements. That's why we are studying now the Jacobian transformation. Dear students, in the next class we will discuss about the how to derive the strain displacement matrix, that is B matrix, for the isoparametric element using the shape function for the isoparametric element, and also Jacobian transformation matrix, that is J11 and J12, J21 and J22. Thank you.